Hey everyone, in this video I'll be explaining the puzzles to day 7 of Advent of Code 2022. If you want to check out my code, it's going to be in the GitHub repository, which is linked to in the description. Today I'll just be sort of talking through the puzzles, explaining what they're asking for, and then explaining my solutions. So, you can check out timestamps in the description and in the chapters to help you navigate around the parts of the video that you want to watch. So now it's time for the time lapse of me solving the puzzles. Enjoy. So today's puzzles were evidently a lot harder because people solved part 1 in, well, the fastest person solved it in 3 minutes, which is unbelievable, and last person solved it in 10 minutes, and for part 2, 100th place got it in 14 minutes. So today's puzzles were definitely a lot harder, and when I saw them, I was kind of intimidated at first. So in total, I didn't place. I took a total of about 20 minutes. 20 minutes to solve part 2, which is still decently fast. I ended up getting, about 300th place. So pretty satisfied with that. That's okay. There's just some experience that I have to gain throughout. Anyways, today's puzzles are a bit trickier, as I said. So the explanations are definitely going to be a bit ramblier, and you might see this as a less polished video. Okay, let's explain the puzzles. So today we are trying to update a device and do it through the terminal. So what we have to do is free up some space in the file system because currently it's too full to do a system update. So we're given a terminal output. Basically, there's a bunch of commands here, and as well as their outputs. So hopefully you're familiar with how a terminal works, but there's a basic explanation here that you can read. The link to the puzzle will be in the description, so you can check that out. Basically, there's two commands that we can run. There is cd and ls, which are the regular Linux commands, or bash commands. They actually also exist in PowerShell. So these are pretty universal commands. cd basically changes where we are within the terminal. So currently we start out at the root directory, which is just /, and then we move around by cding to various directories. We also have this, double dots to go back, or in other words, go up a level in the file system. We also have ls, which displays all of the files in our current directory, as well as any subdirectories that exist. So all of these files are in the formats. You have the size of the file, and then the name of the file. Here's an analysis of that terminal output over here. So we see all of the directories, their subdirectories, as well as the sizes of all the files inside the directories. So our task is to find the total size of all the directories that have a total size of at most 100,000. So the catch here is that, of course, directories contain subdirectories. So when evaluating the size of a directory, you also have to include the size of all the files inside subdirectories, not just the files that are directly under this directory. Okay, so here's my code. I'm going to walk through it a bit. I'm going to talk about, how I kind of approach the problem. You can always check out my code in the GitHub repository, which is linked to in the description, just as a reminder. So the basic idea is, well, first I wanted to parse the input because it's kind of complicated. You don't want to do this manually. You want to be able to separate all of the commands as well as their outputs and just parse them well. So first thing I did, of course, was to do this, Python read input and then parse line. So notice that all of the commands and their outputs are separated by this $sign and a new line. So what I did was I split by new line $space because that just extracts all the commands and gives us a list of strings where each string represents a sort of block of command and its outputs. So this would be a block. This would be a block. This would be an individual block. All of the cd commands don't have outputs, so their block just is the command itself. So I figured it might be helpful if I printed out the first few blocks here. So, actually I lied. It turns out each block is just the string so far. It's not a list yet. So the first 5 blocks here are, you can see the cd command, and then this ls command. So this \n is a new line character. So we have this ls command followed by all of its outputs, and then the cd command, and then this ls command followed by all of its outputs, and so on and so forth. So now we have a convenient list that contains all of the commands and their outputs separated into a list. Okay, next goal, of course, is to simulate all of this traveling around and record the sizes of all the directories. So what we do here is we create just 2 different variables. My goal was just to, directly simulate. We have a list containing all of the previous files or directories So we're going to maintain our current path inside this path variable, and then we're going to just traverse through all of the blocks, simulating where we go and adding the sizes of the files to a variable that later gets stored inside a dictionary. So what we have here is a default dict, which in Python it acts like a dictionary, except it acts like a default dictionary. So if you haven't inserted a key into it yet, you can still assign it and manipulate it and access it. So that's what this is for. It's just like a regular dictionary, except whenever you try to access something, it default initializes to 0. So this is just really convenient if we don't want to initialize all the elements all the time. So next thing we do is initialize this other default dictionary called children, which we want to store a tree, of course, of the directory structure. So what we can have is for every path, we list all of its children inside a list. So this default dict is just a map which maps all of the paths to a list of their children, and this will help us parse later on. So here we go. We're going to parse through each block. This is a function that takes in a string, which is one of those blocks that we talked about previously, and it's going to do some manipulation and return the thing that we want. Or they're not return, but just manipulate this dictionary. So let's break down the code. Lines will split this block into its constituent lines. So we start with ls, and then dir this, dir this, dir this, dir that. The first line is always going to be the command, and the remaining lines are going to be the outputs. In the case that we have a cd command, we actually don't have any outputs. So lines is just going to be a list with one element. And then we have the commands, of course. This is the first element inside that list, and then we have the outputs. This is going to be empty again if it's a cd command. Okay, and now we actually want to parse the command to tell if it's a ls or cd command. So we just split it up by spaces. If it's an ls command, we're not going to have anything other than just the ls here. And then we're going to have a operation variable just for renaming convenience. If it is cd, then all we have to do is change our current path. And how we do that is we look at the second element. If it's a double dot, that means move up 1. So we're just going to remove the last element from this path list. Otherwise, it's cd something, so we want to add that something to our path because that's a valid directory that we can go into. Okay, so if it's a cd command, once we do that, we can just stop. Otherwise, it's an ls command, and we're going to do some stuff. So this slash join path is just going to turn our list, which contains all of our parent directories, into a giant string that represents our current path. So hopefully you're familiar with these. It's just going to look like a big old path. And this is going to be useful for storing stuff inside our dictionaries. So next thing we do is we create sizes. This is not really a necessary variable. We could just make this an int, but I'm not going to change my code now. This is going to be a list containing the sizes of all the files within this directory. So we just loop through all the outputs because we know it's an ls command now. If it's not a subdirectory, then it's a file, and the first part of that line is going to contain the size of the file. So we're going to split up that line by a space, take the first element, or index 0, and turn that into an integer, and then finally add that to our sizes list. Otherwise, it's telling us a subdirectory, so if it is a subdirectory, then we want to add that to our children map. And how we can do that is just create the new path by adding a slash and then the name of the directory to the end of our current path, and then finally add that to the list of children of our current path. Afterwards, we want to update the size of our current directory. In fact, this is just the size of our files immediately contained within this path, so it's not going to contain all of the children yet. We're just keeping track of the direct files that are inside this directory. We're going to deal with the subdirectories later. So now, through this parse function, we have created two maps, or dictionaries. One of them contains the size of all the files immediately within one directory for every directory, and we have this list children, which contains all the paths to subdirectories for each directory. Okay, so how do we deal with subdirectories? Well, we're going to do a depth first search, and this function is going to return the total size of a directory. This thing is called LRU cache. Basically what it does is it caches the results of the function that you write after that line. So in our case, we're mapping paths of directories to the size of all the files, including subdirectories, inside that path. So this cache function is just going to help us not to recompute things, because later we're going to have a little bit of redundancy here. I don't know if this is strictly necessary. It's probably not, but for the sake of safety, I'm adding it. Okay, so to do the depth first search, we're just going to take the size of all the files immediately contained within this directory, go through all the children, add their sizes to our current folder size using this recursive function, and then finally we're going to return the size for use by whatever called this function in the first place. Okay, and now finally we can extract our answer. We now have the size of all the directories, including subdirectories. So what we can do is just simply loop through all of them, find the size of each directory using the DFS function that we just wrote, check if it's under 100,000, and if so, we add it to our answer because that's what we're asked to find. In total, my solution runs in about, let's say, just a couple seconds, so it is pretty fast, even if the parsing and file names and whatever are, path names are pretty long. Okay, so let's take a look at part 2. Part 2, usually it's a lot shorter than part 1, the problem statement. So what we're asked to do here is actually do the update. What we need to do is delete a directory that frees up enough space. So we're given that the total available space in the file system is, I think this is like 70 million, and we need to free up at least 30 million unused space. There's no units here, which makes me slightly uncomfortable, but it's also easier to deal with. So what we need to do is delete a directory that will make the unused space at least 30,000, but we want to find the directory with the smallest unused space because we don't want to delete any more than we have to. So this is relatively simple with the framework that we set up in part 1. All we have to do is figure out how much space there is remaining. So we just subtract the size of the root directory, which is just this regular slash from 70 million. And then to find out how much extra space we need to free up, we can subtract the amount of unused space from 30 million. So now we know how many units of memory we need to free up, and now we just need to find the directory with the path that is at least this amount, at least how much we need, but the smallest amount greater than how much we need. So we initialize our answer at 2 to the 30, just because it's a huge number and will work. Actually, this is probably too small. Okay, we initialize our answer at 1 to the 60, which is an absolutely ginormous number, and this is just going to help us with our min function later. We're going to go through all of the directories that exist. We're going to find the size of all those directories using this DFS function. So the caching comes in useful a little bit here. Actually, it doesn't really, but I just like to include this line for safety. We just check if this directory contains enough files for us to delete, and if so, then we keep track of it as a possible directory and add its size to the answer, taking the minimum of the size with our answer, just to make sure we're freeing up as little space as is necessary. So using the framework we set up in part 1, this part 2 becomes quite easy because we already have all the information that we need and we just need to do a couple of computations up here. Okay, anyways, all of my code is linked to in the description, so be sure to check it out. And I hope today's explanation for day 7 helped. If you have any questions, comments, or feedback, feel free to leave it in the comments below, and I'll see you tomorrow for day 8. Thanks for watching.